About Timmy and messing up and substitution. And so we're going to wrap that up. We're going to do a little bit of work here at the end of 4.5. We'll do 4.6. I think we'll go back and do that one example in 4.4, and that'll wrap up our second unit, which is over chapter 4. So anyway, everything we worked at last time had to do with indefinite integrals, so there was always the plus c hanging there in the end. Our answer was in terms of x's or y's or t's or whatever it was. We're going to do a couple of examples with definite integrals in which there are limits of integration, like for example number 4, 0, and 1, limits of integration here. So we're talking now about areas and accumulating positives and negatives and stuff like that. And so we'll handle these just a little bit differently. We call this change of variables. So I would say that change of variable and substitution are more or less synonymous. We're going to be changing the variables, in this case, from x's to u's, although it could be other letters too. Doesn't have to be used, but that's very common. So let's review a little bit here what we did last time. Whenever you're going to be doing any substituting, we always make the u equal to what? The inside. That's right. So u equals x squared plus 1. And then the du naturally would just be the differential of whatever that is. So 2x times dx. So then as you start to work on substituting, what I'm going to do here is I'm going to just write the integral. I'm not going to put the 0 and the 1 on there yet. We'll deal with that later. But I would write u cubed. And I still have an x and I still have a dx. I can substitute the x times the dx out in one step. What can I replace the x dx with? Not 2 du.
1/2 du.
Yeah, it'd be du over 2, or 1/2 du, equals x dx. 2 du over 4. There we go, over 4. Or 5 du over 10. That's good too. Okay, so then I could then write integral of u cubed times du over 2. And now I'm fully substituted over to u's, except for the 0 and the 1, and this is where we need to focus on, I think. I think you guys were pretty good at that other stuff we just did last time. The 0 and the 1. The 0 and the 1 are related to which variable? X's. They are from x equals 0 to x equals 1. And by substituting u's in for x squared plus 1, we have changed now. Those limits of integration can't be in terms of x anymore. They have to be in terms of u. So whereas before it was x equals 0 to x equals 1, now it needs to be u equals something to u equals something. Does that make sense? So then how do I relate my u's with my x's? Into the u equation, right? So I will do that. So it's the old low limit was 0. Now it's going to be u equals 0 squared plus 1, so that's 1. The old high limit was 1, so that would be u equals 1 squared plus 1, which is 2. So my new limits are from 1 to 2. So it just shifted along with our substitution, shifting things over. So now here's the thing. Once you convert everything over to u's, we're going to stay with u's. We're burning the bridge that leads back to the x's. We're not going back there, right? So it's really easy to kind of do this halfway hybrid thing where it's half x's and half u's, and you get confused and you want to plug back in. We're not going there. Now that we have gone all the way over to u's, we're not going back to the side we were on before. So here's how this would finish. Find our antiderivative, 1/2 times 1/4 u to the 4th, evaluated from 1 to 2, and I will not be plugging back in anything having to do with x. Remember, I burned the bridge that leads back to the x's. I'm staying with u's. So this would finish with 1/8 times 2 to the 4th minus 1/8 times 1 to the 4th. Does that make sense? Leaving everything in terms of u's, plugging in the 2, plugging in the 1, and evaluating. So this is going to give me 16 times 1/8 is 2, 2 minus 1/8. I'm coming up with 15/8 for my final value. Any questions there? Is anybody tempted maybe at some point in there, maybe right here, to plug the x squared plus 1 back in for the u? It's tempting. I've seen a lot of people do that. They're used to doing that. Go ahead.
Could you do that and use the original limit?
You could use the old limits, 0 to 1, but that's like even more work, right?
Yeah.
and more things to keep track of, but you could do it that way. Yep. In fact, this one is actually easy enough. The antiderivative is easy enough. You could just do the whole Timmy messed up the chain rule thing mentally and leave everything in terms of x. So, yeah. All right, so this skill using substitution is definitely important, and Brandon's question is really good. Like, you could do it the way he was describing, except in case of example number 5. So if you look at example number 5, this forces you to know how to do substitution. So take a look at this one. This is a really, really common question. Example number 5, and I'm going to let you guys think this one through on your own, and then we'll answer it here in a second. Which of the following is equivalent to that integral you see right there? So this will take a little bit of work with substitution to be able to come to a conclusion. So give it a try. We'll check your answer in a second. Hey, I do have a question for you. I don't know the answer to this. Curious to see what you say. If this were calculator active, what would you do? Hey, I got a question for you. Sorry to interrupt, but I'll do it anyways. If this were calculator active, what would you do? You think that'd be faster?
Math 9.
Couldn't you math 9 all of them and see which one equals the original one?
Yeah.
You could be pretty fast, especially if you, u to the 7th, that's pretty easy to plug in. It's debatable. You could go either way. I don't know. All right, so here's what we're going to do. Could you guys be quiet, please? Thanks. All right, so u equals the inside, x cubed minus 1. Du is equal to 3x squared dx. So we're going to use that as a basis for our substitution. And so we're going to go integral of u to the 7th. And we've still got that x squared dx hanging out there. What could I replace the x squared dx with? Yep, if you just divide both sides by 3, you get a nice substitution. And so then we get integral of u to the 7th times du over 3. And it'd be really easy at this point, and I say this for a reason, because I see this stuff all the time. It'd be really easy to be like, oh, look, there it is. Everything matches up perfectly. It's 1/3, just like I've got. The integral from 1 to 2 matches the original integral from 1 to 2. It's u to the 7th. I must be right, except
You're a slacker.
I'm wrong. I'm a slacker. I need to check my limits. My old limits were 1 and 2. And so to check my new limits, I've got to run them through this. So I'd say my old low limit would be u equals 1 cubed minus 1. Transformed into a new limit, it's 0. And you could actually answer the question now, couldn't you? There's only one good answer. You try the other one, u is equal to 2 cubed minus 1, which is 7. Now it's clear. Integral from u to 7, or from 0 to 7 of u to the 7th du, all divided by 3. So your answer has to be C. Okay. Any questions? Okay, fantastic. Let's check out where we are. We did evens and odds last time. I think we've done everything up through here, right? Let's flip over to 4-6. This will be quick.
So when is our test?
It's not this week. It's next week. Because,
What I like to hear.
yeah, because I knew we'd be finishing up today, and then I was like, I don't want to just like have one day in between. I'd rather give you some time to study. So a week from this Wednesday.
A week from, okay.
So like
perfect.
9 days away, 8 days away.
Perfect. We had a math test today in my dream last night, so I thought I would ask.
Oh man, you gotta keep the dream world and the real world
Yeah,
separate, right?
it freaked me out.
Yeah. Okay, we're going to continue our discussion of approximation. It's going to be very brief here. Numerical integration, we've actually done some of this already. We have done left sums. Left sums look like this. We've also done right sums, and right sums look like that. So this is a combination of left sums and right sums here. We have even done midpoint sums, which look like that, and maybe like that, and that, something like that. Every single one of them has involved a rectangle, correct? Trapezoids tend to be better, don't they? So a trapezoid would look like this, where you've got this nice slanted top part, and then another slanted top part, and then maybe one more of those. We'll go with 2 more. something like that. You get this nice approximation. Trapezoids tend to be a lot more accurate than a left sum or a right sum, and maybe even a midpoint sum as well. So that's what we're going to be using is trapezoids. And as I mentioned before in previous classes, there we go. Sometimes for you high-level math people, the hardest thing is remembering what the area formula for a trapezoid is. Right? Like if you just knew that, it would be really, really easy. So we want to remember that. The area of a trapezoid is A equals, if I remember, Alex was really good at remembering these last year. Am I right? Was that you?
Don't look at me.
No, I can't remember. Does anybody remember? Josh, do you remember?
All times b minus a.
Times height.
Yeah.
I'm going to use more of like the more informal geometry, but you're giving me sort of a trapezoid rule.
1/2 base times height 1 plus height 2.
We'll say that again?
1/2 times the base times height 1 plus height 2.
Yeah. Well, it's actually usually
Like either.
it's usually base 1 plus base 2.
Yeah, but
We usually look at it like that. If you can keep what the H's and the B's are, I know that's weird looking,
I
right?
just do it like the other way.
Yeah, I hear you. Because that's the way it's oriented, it looks that way. Okay, so H stands for height. The B stands for base. What's tough about this, of course, is this is all based on the traditional geometry view of a trapezoid in which the two parallel sides are horizontal. Of course, when you look at the way that we use the trapezoids here, the two parallel sides are not horizontal, they're actually vertical. And so your height would be here. This would be base 1, this would be base 2. So what's tough is it's like the bases in the formula are actually heights, the way we have it arranged, and the base is actually a height. It's flipped around, like flipped 90 degrees, rotated 90 degrees. So we want to be able to remember that formula and be able to use it appropriately. So I've mentioned stuff like this. I think I mentioned this last year. There is such a thing, if you look in your book, as the trapezoid rule, and that's a thing. It's a very worthwhile, usable thing to use, except somebody ruined it for everybody else. Somebody wrote a program in the past, and they gave it away or sold it. And so people that really had no idea what they were doing were able just to purchase a program, making it look like they knew what they were doing. It was an amazing program. I think I shared this with you. It would not only graph the curvy graph that you're graphing, it would give you a picture of all the trapezoids, it would give you all the steps that you would need to write down in order to do well in some FRQ like this, and it would give you the answer too. So all you had to do is plug in a couple of things, it would do all the work for you, and it looked like you were really, really good at it, when in essence you had no idea what you were doing, other than you just knew where to plug a couple of key things in and just did all the work for you.
Calculator?
On like a TI-84.
That's a wicked program.
I had a student, you can program some amazing things in your calculator. So here at Valor, we used to have a 6-day rotating schedule. I don't think any of you have ever had that. So we had a 6-day rotating schedule with 7 classes, and so every week was different. I personally liked it because I liked the variety of it all. It never felt like any week or day was ever the same. But then you had to pay careful attention to what was going on, right? My point with all this is to say that I had a student that was so good at programming. He took his TI-84, like the typical calculator that we have, and he programmed the 6-day rotating colored schedule into his calculator. Not his phone or a computer, but his calculator with a little graphic and everything with various shades. It was like a black and white screen. It had these various shades of gray that made it look like, he could tell you what color it was supposed to be. And that was a little bit of a stretch, but the whole calendar rotating thing was spot on. It was amazing. So you can program a ton of stuff if you know what you're doing, which I don't purport to know what I'm doing on that. So it was absolutely amazing.
I downloaded Matt King's programs on my calculator, and then every day my RAM would clear.
Oh no.
I don't know what he did.
Well, he gave you a virus.
Yeah.
Yeah.
I think
That
he
was,
gave my calculator.
and you act surprised?
No.
Okay. So guys, hey, listen up. I say all that to say this. A question like number 1, I leave this in here just as an instructive comment. You will not see a question like number 1. So number 1 is using what's called the trapezoid rule, in which if you just memorize a formula and you just start plugging some stuff in where it goes, or you have a formula and you just start plugging the few things in where they need to go, you'll get this right answer. You will not see a question like that because you're not tested on the trapezoid rule. You are, and you will definitely be assessed on things like this, where it doesn't say use the trapezoid rule or in equal sized intervals. It'll give you a table. This is the most common way to do this, simply because the table is completely unpredictable. You can't write a program for it, and so they're able to see, hey, do you know how to do this with trapezoids without allowing someone who has a program to make it look like they know what they're doing when they don't. So I am going to take a few minutes. We'll draw some pictures of this, just hopefully to help a little bit. It says a certain function f of x has this table below with all the values. Approximate the integral from 2 to 17.
Are we doing 6 integral?
We're just doing however many we have. So 2, 3, let's see here, 1, 2, 3, 4, 5, 6. Yeah, so 6. Yep. Unless you're otherwise told, we'll use like all of the intervals that we're given. That's a good question. So maybe you draw a picture. I'm just thinking for sure, for somebody like Jaden or Jeff, maybe a picture is wise. So I'll at least draw a part of this. So let's see here. 2, 3 would be like right here. 3, 4. 2, 3 would be like there. 3, 4 would be up there. So on and so forth. 5, 8. 8, 17 would have to be way up there. There's 10, 13. 12, 9. And finally 17, 3. Does that make sense as far as just plotting those data points? It goes up and then it goes down. Pretty simple. So can we know for sure that the graph does this? Do we know for certain? We have absolutely no idea. I mean, it could be crazy. It could go up, down 20 times between each of those data points, right? Or 100 times, or 1,000 times. Or it could be piecewise linear. We don't know. It could be piecewise parabolic. It could be a crazy graph, or it could be a simple graph. That's all we know. So I am just going to sketch something in just as sort of a what if, maybe it does something like this, and then it goes up and around and whatever. Just make it a representation of it. You don't even have to sketch that in. All we really have to know here is that we're going to be using trapezoids to approximate this integral. So here are my trapezoids, or at least a couple of them. There's my first one. So Jaden, I want to make sure you get this, because I feel like we hammered away at this enough last year where these folks are going to remember it pretty quickly. So this right here is my height, even though it's horizontal. What would that be?
For the first one, you
Say again?
1.
It'd be 1, yep. And then the two bases would be 3 and 4. That's right. So 3 and 4. And then you draw another trapezoid, maybe like right up here. You already know that the left base is 4. The right base would be, that's right. And the height would be, from 3 to 5, it would be 2. So then, maybe you start building this out and you start doing some calculating of areas. So we could say something like the integral from 2 to 17 of f of x dx is approximately, and then I can start doing that trapezoidal area formula. So it's going to be 1/2 times 1 times 3 plus 4 as I apply that formula. Does that make sense? Okay. And then be plus 1/2 times 2 times 4 plus 8. And then you just keep rolling all the way across. And the hope is that you can do this without drawing a picture. That you could look at the table and see the difference in the x's will be the height, and the two different y's will be the bases. So if you keep going, it would be 1/2 times 3 times 8 plus 17 plus 1/2 times 2 times 17 plus 13, and then 1/2 times 2 times 13 plus 9. The last one would be 1/2 times 5 times 9 plus 3. So kind of a finer point here as far as getting credit for any of this. I'll tell you right now that if you're asked to do a trapezoid approximation, one of the 2 points is certainly going to be, did you do a trapezoid approximation, like evidence of a trapezoid approximation? That right there is evidence of a trapezoid approximation. right? So if you are in the habit of doing some math ahead of time in your head where you like, maybe you look at that first one and you're like, oh, that's basically 1/2 of 7, 3.5. And then, hey, half of 2 is 1, 4 plus 8 is 12, so plus 12. This is not evidence of a trapezoid approximation, is it? This is just a series of numbers being added up. And so as far as presenting your work, even though you're probably plenty good enough to do all that arithmetic in your head, take the time to present. I'm doing trapezoids here. Look, there they are. And then if you want to do all the arithmetic in your head, that's fine. If the calculator's active, maybe use that. Does that make sense? So what'd you guys get for a full sum on the trapezoids? 135? You guys get 135?
Yes.
Okay.
You're right.
If it's multiple choice, you absolutely have to. If it's free response, no. But if it's free response, then you don't have to show the whole trapezoid thing, but you do have to have an exact answer. So it's like, it's one or the other.
Sure.
Yeah.
Just do both.
Or you could just do both, but doing both is a risk, because if you make a little arithmetic mistake, now you're out the answer point. It's like, yeah, okay. All right, guys, questions, comments, concerns? Liz asked a good question, something you'd all probably be interested in. She said, when would be a test over this? Because we're basically done with 4. We're going to go back and review an old thing in 4.4 right now. The test on this is 1 week from Wednesday, so like 8-9 days away. So it gives you plenty of time to practice and maybe ask some questions, get yourself all the way ready. We'll keep moving into 5, but we'll do that test next Wednesday. You good?
So that will be chapter 4 test, and we're starting chapter 5
Tomorrow.
tomorrow.
Yeah, so we'll do that. We'll push ahead, and it's all related anyways, and so
Yeah.
like it's not like we won't be doing, the chain rule with integrals and all that stuff. So it's a good review, but we will push ahead for sure.
Fine.
Okay, let's go back and let's do a little reviewing. I would like to go back to, this is in 4.4, so I'm going back a ways. I would like to do, back here, example number 4, back in 4.4. It looks like this. We never really did this one. We skipped right over it, and I said, we'll come back to it. Now we're coming back to it. Yeah, Brandon.
Is this unit going to be similar to the last one where the extra practice counts as a case group?
Yep. That'll be true of this, and it'll also be true of the next unit, but then the one after that, no.
Because we'll have the actual quiz.
Because it'll be like real quizzes in the middle. Yep. Because it'll all be 100% new for everybody. Yeah, Liz. That's good. That's good. Can you letter A. Guys, some really interesting questions came up here when we were working on letter A. And so I'm just going to use the space down below, and then I'll erase it as we move on to the next one. So for letter A, it says find the values of f of -6 and f of 5. You have that graph of f prime. So anytime you have a graph of f prime, but you want to know about f, aren't you going to have to do some kind of an integral in there somewhere? So that's where I'm going to start here. And I'm going to start with this. I'm going to say for A, I'm going to go integral from -6 to -2 of f prime of x dx. And I need to say what that equals here in a second. But why on earth would I pick -6 and -2 for my limits of integration? -2 is given, and -6, I want to know. That's right. So what does this equal? Does anybody, I don't know if you guys wrote it out this way or not, but symbolically, what does this equal? No, symbolically. I realize we'd use maybe some areas to do this, but using symbols.
4 and
That's, well, not that symbol. Not a number.
oh, f of -2.
There we go.
Minus f of -6.
There we go. So using FTC 1 and 2, that's what that would result in, right? So the antiderivative cancels out the derivative, and you find the difference in the evaluations from the upper minus lower, essentially. That makes sense? I really like using this because I think it gets all this stuff right out there in the open for us to use. I know that f of -2 is 7. I know that f of -6 is what I'm trying to figure out. But then to figure out the value of that integral, that's where you've got to use some areas. So if I'm going to go from -6 to -2, all that is a triangle, right? 4 by 2. You guys get an area of 4?
Yeah.
Okay, it's positive 4. So 4 equals 7 minus f of -6. So I'm getting 3 equals that. How are we doing? Jaden, you nailed it? Good? Colin, we good? 3? Okay. So then, we're also supposed to find f of 5. So what I'm going to set up here is the same kind of integral, the integral from -2 to 5 of f prime. This will equal f of 5 minus f of -2. And once again, I know that f of -2 is 7. I know that f of 5 is what I am trying to find. But now I got to accumulate from -2 to 5. And this is a little bit different. So this is a semicircle, radius 2. What do you guys get for an area there? 2 pi. So the area is 2 pi, of course. We're going to accumulate from left to right. That'll be negatives accumulation. When it comes down to it, this is a triangle from, let's see, the base is 3, the height is 2. Did you guys get an area of 3 there? Okay. So then as I accumulate from -2 to 5, this would be -2 pi plus 3 equals that. And then to finish this off, I just add the 7 over, so it'd be -2 pi plus 10 equals f of 5. We just leave our answer like that. Questions, comments, concerns? Where are we at? I had a really interesting conversation with Dylan. He asked a really great question. He did something really similar. He set up his integrals a little bit different from mine. So he set it up as integral from -6 to -2 to -6 of f prime. Yeah? Is this the one we were talking about, right? Yeah. And so he said, okay, well then this is equal to f of -6 minus f of -2. And he was having a hard time like, hey guys, this is worth your while. Really is. He was having a hard time understanding how the numbers would all work because that seems reasonable, right? Did you notice how the low number is actually numerically higher?
Yeah.
So instead of accumulating from left to right, he's accumulating from right to left. He's going the other way. And so let's talk a little bit about why. Let's get this right side straightened out. So f of -2 is 7. But then for the left side, since he is not accumulating from left to right, he's accumulating from right to left, we automatically would say, well, I don't know, that area, of course, we know that this area right here is 4. But if I accumulate from right to left, that would accumulate as a negative, wouldn't it? So my question to you is, why? Why on earth does accumulating from right to left mean that above the x-axis means negative and below means positive? But if you accumulate from left to right, above means positive and below means negative. Why on earth would that be? And you know the answer, so don't say anything yet. Let's make them think. Do you understand the question? Accumulating from left to right, basically stuff above is positive, stuff below is negative. The other way, it's reversed. Why would that be, Liz?
It's like if you were, like say this was a velocity graph,
Okay.
and you were like walking forward.
Yep.
You would like say you walk forward like 4 feet. And so it would be like if you started at the like 4 foot mark.
Your
and
finishing
then
point.
Just like, yeah, if you started at your ending point.
Okay.
And then like even though you moved forward, it's like you started at your ending point and then you were like reversing it.
Okay.
So you still moved the like the same distance.
Yeah.
But you were moving from a point that was further ahead to the point that was behind it.
Having to do with the times, right?
Yeah.
Yeah, okay. I like the analogy. I think that's really good. How does it apply to this? Because this doesn't have anything to do with times or velocities. It's a good analogy. I like it. But what about this? It's a good, really good start. How would that work with this? Why does the plus minus switch when you go from left to right versus right to left or whatever? You understand? Any ideas? There's a very, I think, a very concrete answer for it.
Because going one way, f prime is increasing and it's decreasing the other way? What is that?
Right. Well, so increasing, decreasing is always judged from left to right.
Yeah.
Always, yeah. So we would never look at this and say, hey, this part right here is decreasing. Oh, but if you went the other way, now it's increasing. I don't think, we always judge that sort of terminology from left to right. You're like, you're kind of there. Come on. It's easy for me just to tell you the answer. It's better if you could come up with it. It's like you're running back, and that's kind of what Liz said. It's like you're you're looking at your old, like your new position is your old position, kind of, and yeah. All right, well then let's do this. If I look at this in terms of rectangles, so let's say that I just did like a left sum on this part. What would be this length right here? This base length. If I did left sum, the way that I drew that, wouldn't the base would be what? 1. Okay, and the height would be 2. So the area of that rectangle would be 2. Now, all of this hangs on one thing. You told me that the base length was 1. So how did we get that? How did we get the base length of 1?
Because there's one space between.
Right, but as far as accumulation, weren't you going a very specific direction from left to right? So this over here is -6 for the x-coordinate. This over here is -5. So if I did -5 minus -6, I get 1, don't I? So if I accumulate from left to right, we think of the right edge as like position 2, like the final position, like you said. And we'd think of the left edge as position 1. And so we'd say the base is positive. And that's if you're accumulating from left to right. If, however, you decided to accumulate the other way, these are still those numbers, right? But now the second position versus the first position is now reversed. And so you wouldn't say this anymore. You would say, well, it's actually -6 minus -5, and that ends up being -1. So if you accumulate from right to left, all of your bases are negative, while your heights remain as they were, either positive or negative. And so when you think about this, if this really was a -1 multiplied times a +2, now the area would be, or the area, if you will be -2. And so if you accumulate from right to left, all of the things that used to accumulate as positives would now be negatives and vice versa. That's kind of the why. But that makes sense. He was right on it. He just was kind of wondering, why is it like that? It's a great question to ask, for sure. Okay. We okay with A? That was a longer explanation for A, but I thought it was worthy. I thought it was a great question. Okay. We good? Okay, so then B. Let's just do that. So B says, on what intervals is F increasing? And a couple folks made the comment they felt like A was fairly difficult, especially compared to B. They're like, oh, B was really easy. Maybe you felt that way, maybe you didn't. Maybe you thought it was the other way around. But I think that they're hitting at different things for sure. Right? So for B, on what intervals is F increasing? Any suggestions? Where F prime is positive. So basically wherever we're above the x-axis on the F prime graph. So that would be the interval from -6 to -2, and the interval from 2 to 5. Because F prime is positive on those intervals.
Does it have to be closed intervals?
Technically, it's supposed to be closed, but we'll take open.
Well, AP.
Yep. There's only a very small handful of scenarios where open and closed get considered, and we'll look at some of them this year, but there will be a very clear way to decide. There's enough argument about this where they just don't go there.
Okay, perfect.
Yeah. Okay. Questions on B? Alrighty then. So then C says find the absolute minimum. So those are some really key words, absolute minimum. On this interval, -6 to 5. So they're giving you two really large hints. You got to find global extrema or absolute extrema. They've given you a closed interval, and they even use the word absolute, right? So they're trying to make it super clear. We need to consider the endpoints as well as critical numbers. So that's what I'm going to try to do. So my candidates, the candidates test here, my x's are going to be my candidates. What do you guys see as viable candidates besides the -6 and the 5? -2 and -2 and 2. Yeah. So basically, I've got all my critical numbers, both of them, and my two endpoints. And that's it. Any questions there? Which one could you just dismiss immediately and say that's not the min? -2. Why could you just say -2 is not it? Yeah, it's that sign change thing with F prime. So you could say that -2 for y equals f of x, that's going to be a relative max, therefore clearly not the min. And so yeah, I think it's always good practice to address it. If you just wanted to calculate the value, I mean, that'd be fine too, but you just put its relative max, therefore it's certainly not going to be the min. We already figured out two of these, didn't we? What is f of negative 6? I already forgot. 3, and the other one had a pi in it. 10 minus 2 pi, okay. So then the only thing we got to really work here for is the x equals 2. So in case maybe you're wondering, we got those from part A, right? In part A we found those. So for 2, what would I set up to help me find the value of f when x equals 2? Yeah, integral from negative 2 to 2. So integral from negative 2 to 2 of f prime of x dx. I would set it up the same way as was suggested earlier, equals f of 2 minus f of, let's try that again, minus f of negative 2. I already know that f of negative 2 is 7. And the antiderivative, the integral from negative 2 to 2, that's just the circle, isn't it? Or the semicircle. So negative 2 pi. So negative 2 pi equals, so I'm going to get 7 minus 2 pi for that. So I plug that in. Here's where a little bit of estimating will go a long way, right? Pi is approximately 3, right? It's a little bit bigger than 3. So 7 minus 2 pi, slightly less than 1, right? And then 10 minus 6-ish, be slightly less than 4. So isn't it pretty clear then what the min is? What would you guys say the min is? Yeah, 7 minus 2 pi. You don't have to be, you don't have to list the approximation out. Like I said, I think this is a no calculator question. So you do want to call it out. So just say something like the min is 7 minus 2 pi. Don't just leave it sitting there in the table. Call it out. Say that's the min right there. All right. Any other questions, comments, thoughts? All right. So then finally D says for each of f double prime of negative 5, f double prime of 3, find the value, explain why it does not exist. So does one of these not exist? Which one is a DNE? Okay, we'll get there. Yeah, we got the doink point there. Yes, for sure. So let's figure out the one that actually we have an existing value. That would be f double prime of negative 5. So how does f double prime relate to the graph of f prime? It's a slope. Yeah. So what I want to do here is look at negative 5, which is right here on the graph of f prime, and ask myself, what is the slope of f prime, aka f double prime? What's the slope of f prime right there? Well, thankfully they gave us a nice piecewise linear part, so this is pretty easy to figure out. It looks like it goes down to right 4. So you guys get negative 1/2? Yeah? Okay. So negative 1/2 for that one. And then you said f double prime of 3 does not exist. Why? Because it did say explain why. Yeah. So let's talk about your options here. If you said this, sharp point.
Yes, full credit.
Not full credit, unfortunately.
Full credit.
Every now and then they'll give like a partial credit for something like that, but
F prime is non-differentiable.
well, that's circular reasoning. You're saying you can't find the derivative doesn't exist because it's not differentiable.
Yeah.
That's circular reasoning. It's like saying Liz is awesome, well, frankly, because Liz is awesome.
See, I don't see the
It's
issue.
like around and around we go. Well, it works for you. It doesn't work for math, right? For math, they're going to be a little more rigorous. We're all willing to accept that, I suppose. But math, they're going to be a little tougher, right?
Okay, that's fair.
So because it's a sharp point, I heard Colin back there using a key word.
Limit.
Not that, Jack. Limit, yes. So we could say this, and we could get pretty specific on this one. I don't know. I don't remember what year this is from. I don't know how specific they wanted you to get. But you could say because the limit as x approaches 3 from the left of f double prime, right? Because we're talking about the slope of f, right? So from the left equals, well, gosh, from the left that's linear, isn't it? And it looks to me like it has a slope of 2. So you could say that from the left, I'm going to give myself a little bit more room here. I don't think I can do that. Okay, so let me try this. I'm going to say limit as x approaches 3 from the left of f double prime of x equals 2. And then the limit as x approaches 3 from the right of f double prime, what does that equal? Is that right? Negative 1. Yeah. 2 halves, negative 5/5, also good. Those two things are clearly not equal to each other, right? So in other words, the slope of f prime from the left and the slope of f prime from the right are not equal to each other, and that's enough right there, okay? So in some years, if you say there's a sharp point or a sharp corner or something, that would give you like a partial credit somewhere in there. They'd give you like 1 out of 2 points or something. But this would be a much, I forgot my of x. This would be a much more rigorous way. Yes, ma'am?
So for explaining it, would it be okay if we just said, like the limit of x, or limit of f double prime as x approaches 3 from the left is not equal, like the limit as...
Yeah, so I think they usually will bend to that and give you credit for that. Instead of saying 2 and 1, what if you said positive and clearly negative? That'd be like a middle ground between what you said and what I said.
Okay.
Probably be a little bit better, I suppose. So be as accurate as you can. And if it's piecewise linear, it's like pretty easy to find the slope. If it's curvy, then you really have to go with the positive, negative, perhaps. Typically, they'd be okay with that. Yeah, great question. Okay. So let's see here. A couple of things I just want to mention to you guys. Again, just a reminder that our test over this material is not in 2 days. It's in 9 days, I guess. And so please consider that as we move forward into Chapter 5. Also, Unit 3, which covers Chapter 5 in your book. Listen carefully, please. It covers all the transcendental stuff, so like e to the x, natural log of x. We do inverses and arcsine, arctangent, and all that stuff. There is going to be one of those little sections in there that's like a bonus topic. Let's see, what is it going to be? I think it's going to be, I think it's hyperbolic sine and hyperbolic cosine, which is something you've probably never heard of before. It often covered in, it's really not that hard. You just never heard of it before. That's just one of those things. It's really not that difficult. Just once you see it, you'll be like, okay, I can do it. That's one of the topics in Unit 5. And then after Unit 5, Chapter 5, we're actually going to go for our next unit into brand new material for everybody. So everybody will be in the same boat. Never seen it before, probably, and so we'll all be on equal footing, I think. So, anyways, it'll be Chapter 8.
Why don't the chapters in order?
To keep you entertained.
Okay.
All right. Have a wonderful rest of your day. See you on Wednesday.
I'm not